2301, as well as kind of the start of 2302, will be understanding ortho, meta, and para substitution on aromatic rings, as well as kind of identifying the strength of nucleophiles. So how strong is a nucleophile based off of electronegativity of the atom that is attacking, as well as things like charge or a lack of charge. We're going to be thinking about things like that today, and how can we potentially introduce something else into the reaction in order to make a nucleophile stronger. The learning objectives that we will be covering today are going to be 19D, which is predicting the pKa for substituted benzoic acids. So again, kind of an extension of what we were talking about last lecture, where we were just talking about carboxylic acids. Predicting pKa trends for dicarboxylic acids. And then afterwards, we're going to have a little bit of review where we will compare and contrast the mechanisms for acetal and imine formation. Okay, so let's start by first talking about learning objective 19D, which is predicting pKa trends for substituted benzoic acids. And this is from section 19.6 in the book. So this may or may not be a little bit of a new word for you, but benzoic acids. Sounds very similar to carboxylic acid, but what exactly is a benzoic acid? Well, a benzoic acid is a type of carboxylic acid, specifically one that is bound directly to a benzene ring. Okay, so that carbonyl carbon in the middle is bound to a benzene ring. And again, the name for this is benzoic acid. Now, similar to a regular carboxylic acid, benzoic acids are quite acidic. And in the presence of a relatively basic species, such as water, we can remove a proton from benzoic acid to form a benzoate anion. Okay, with water, with hydronium as your counter ion. Now, this benzoate ion, similar to a regular carboxylate anion, remember that 8 stands for an anion, is stabilized by resonance. So we can draw a resonance structure for this. To give us another viable structure for our benzoate. All right? So, benzoic acid, we've identified that it's acidic. We've also compared it to a regular carboxylic acid, such as acetic acid over here. If we want to talk about pKas, the pKa of benzoic acid is 4.2. Now, you may think to yourself, that's a little different from the pKa that I remember from our carboxylic acid, and you would be right. If you recall from last class, the pKa of acetic acid is approximately 4.7. Now, this is not an unintentional difference in pKa. There actually is a reason for this. So let's identify some reasons why or why not that benzoic acid may be a little more acidic. Remember, lower pKa means more acidic than a carboxylic acid. So why the difference? Okay, so maybe the first thing that could come to your mind is, okay, we have a benzene ring now, so maybe we could have some extra resonance effects. Well, is that true? If I went and I tried drawing a resonance arrow into my aromatic ring from my carboxylate ion, what you would actually see is that that carboxylate ion is too far away from that benzene ring. You have 2 sigma bonds in the way. Therefore, it cannot resonate into the benzene ring, and that means that resonance is not actually a factor that would stabilize. So this cannot resonate into the ring. Okay, we actually have to go and look at this from the perspective of what is directly bound to that carboxylic acid. Okay, and we can look at this by identifying a key difference between that carbon next to the carbonyl. Okay, and the difference is hybridization. In benzoic acid, the carbon that is adjacent to the carbonyl carbon is sp2 hybridized. whereas that same carbon on acetic acid is sp3 hybridized. Now you may recall that sp2 versus sp3, sp2 has a little more s character, and a little more s character would actually make a species more electronegative. Therefore, it will have more of an electron withdrawing effect. So here we have an inductive effect. Specifically, where sp2 is more electron withdrawing than sp3. Now, I want you all to hold that thought because this is going to be kind of a trend similar to what you saw on Friday that we're going to be seeing for the different acidities of the carboxylic acids that we'll be seeing in this lecture, okay? So think to yourself, inductive effects will be somehow be responsible for the changes in pKa that you may see from a standard carboxylic acid, or now in this case, a standard benzoic acid, okay? So now, because we are talking about benzoic acids, we're talking about aromatic rings. Of course, you could think back to how we manipulated our aromatic rings earlier in the course, and we did so by introducing substitution. So substituents on your benzoic acid can be ortho, meta, or para. Okay, remember this terminology from EAS and NAS. Okay, so whenever we're thinking about something that's ortho, meta, or para substituted, remember these are relative terms to another substituent that is present on the ring. Okay, so here is just a nice and simple benzoic acid. Okay, remember that the position next to the carboxylic acid is going to be ortho, then you have meta, and then finally you have para. And I'm going to write the pKa of benzoic acid here once again, because we're going to be doing some comparisons as we add some more substituents on here. So recall that pKa is 4.2. Great, so now let's take that same benzoic acid and I'm going to add a fluorine atom to it. Now you may recall that fluorine, because it's the most electronegative atom in the periodic table, is actually quite electron withdrawing. Okay, not the best electron withdrawing group that's out there, but it's a pretty good one, and it's more electron withdrawing than just a simple hydrogen. So replacing a hydrogen with a fluorine will actually affect your pKa, and it will bring it down just slightly to about 4.1. Now let's look at another example. Let's say that we have another benzoic acid, but instead of having my fluorine para, I'm going to have my fluorine now ortho to my carboxylic acid, okay? Now that fluorine is a lot closer. You may recall last lecture that whenever we had an electron withdrawing group that was closer to your carboxylic acid, you would actually go and make the carboxylic acid more acidic. The pKa would go down quite a bit. And we do still see the same effect here. So yes, in the same fashion that we saw last lecture, pKa now 3.3, we can actually see that proximity or the distance between the carboxylic acid and the electron withdrawing group matters. So the distance does matter. And you're going to end up seeing that ortho has the greatest effect. On pKa. And likewise, meta and para have a relatively similar effect on pKa. So you wouldn't see that substantial of a difference in pKa between a meta and a para substitution on your aromatic ring, okay? Now, another reason you may say that this works as well is sterics. However, if you look at a fluorine atom, fluorines are actually quite tiny, about the same size as hydrogen. So sterics isn't really playing a factor here, okay? Whenever you're thinking of sterics, you want to think of something much larger like a tert butyl group, okay? But fluorine, is small. Sterics is not a factor here, but electron withdrawing ability certainly is a factor. And on the topic of electron withdrawing ability, let's add another, or let's use a different electron withdrawing group. Let's say a nitro group in this case. Here we have a para-nitro group, and that pKa ends up being approximately 3.4. All right, and if we bring that nitro group even closer, that pKa goes down even further to 2.2. Okay, great. Now this confirms once again the fact that distance does matter, but now a nitro group is actually more electron withdrawing than a fluorine group. So that means that the strength of your electron withdrawing group matters as well. Okay, and remember that works because a nitro group is a stronger electron withdrawing group than a fluorine. All right, so now that we've understood a little bit about how electron withdrawing groups and distance can affect our pKas, let's go ahead and do a chime-in question to extend our knowledge a little bit on what's going on here. Okay, so I'm going to go ahead and open our chime-in question. I'll give you all a couple minutes to think about this. Give you guys another 15 seconds or so. All right, so let's check out the results. Awesome. Okay, so it looks like the majority of the class chose B. We also do see a little bit of preference for D as well. Okay, so this isn't quite necessarily something I've talked about yet, so let's discuss. Is it B or is it D or is it something completely different? So we had 4 choices here. We had just regular benzoic acid. We had benzoic acid, but every position on the benzene ring was completely substituted with a fluorine. We have para-fluorobenzoic acid, and we have orthofluorobenzoic acid. So what I like to do when I'm ruling out which of these could potentially be the most acidic is to first identify electron withdrawing groups, okay? And here we have cases where we either have no electron withdrawing groups or we have at least one electron withdrawing group, okay? So let's go and identify what we have. So first, benzoic acid, not counting the carboxylic acid, which in itself is an electron withdrawing group, we have no electron withdrawing groups. We have a completely substituted benzoic acid. We have 5 electron withdrawing groups here. And we have 1 electron withdrawing group on the next one and 1 electron withdrawing group on the next one, okay? So in thinking about the presence of an electron withdrawing group, we just discussed that if there is an electron withdrawing group, that will lower the pKa a little bit, okay? So that means that with no benzoic acid, or with no substituents on the benzoic acid, that means that just regular benzoic acid will be the least acidic and it will have the highest pKa. All right, I'll label this A, B, C, and D. Okay, now 1 versus 5. Well, if we're introducing just 1, then adding several more is going to actually significantly increase the electron withdrawing capabilities of that ring. So that means that when you have 5 electron withdrawing groups, you're now going to make this way more acidic. And it's going to have the lowest pKa. Now we have the case of 1 electron withdrawing group each. Remember that if you just have 1 electron withdrawing group, and it's the same one, we just have to look at distance. And we see that, remember that if it's ortho, it's going to be closer. And if it's ortho, it's going to be more acidic. And if it's para, it's going to be less acidic. So para less and ortho more. So if we had some sort of an acidity ranking question, we would go and then start ranking this in order of, let's say, highest to lowest pKa. Okay, we would say that our highest pKa would be A. And then the next highest pKa would be the ortho one because it's 1 substituent, but it's farther away. So sorry, the para one because it's more substituted, but it's farther. 1 substituent, but it's farther away. Sorry. Then the ortho one afterwards, 1 substituent, but closer. And then finally, the one with several different electron withdrawing groups on there. All right, any questions? All right, let's go ahead and move on. So let's segue a little bit out of benzoic acids and talk now about dicarboxylic acids. So this is learning objective 19E, and this is predict the pKa trends. Of dicarboxylic acids. Okay, and this is 19.8 in the textbook. So when we're talking about a dicarboxylic acid, that means that we have 2 of the same group in the same molecule. So I'm going to draw out the simplest dicarboxylic acid. This is actually a compound called oxalic acid. All right, so again, 2 carboxylic acids in the same molecule. In this case, we have a completely symmetrical molecule. So we have 2 acidic sites. And in the case of the fully protonated version, so we haven't deprotonated anything yet, we could choose either one. Okay, whether we choose 1 carboxylic acid or the other, for now it'll have no effect. All right, so let's treat this in the presence of something relatively basic. Again, let's say we have some water laying around. Now, if you have a dicarboxylic acid, that means that you have 2 acidic sites, like I said, so you're actually going to have two pKas, okay? The first pKa will be the first deprotonation, and the second pKa will be taking that intermediate, that monodeprotonated species, and then deprotonating it again a second time. So I'm going to call this first pKa pKa1. And we're going to end up with a species that looks like this. So one is the carboxylic acid, and one is now the carboxylate with H3O plus hydronium laying around as our counter ion, okay? So we remember that up to now, most of the carboxylic acid pKas that we've been seeing have been in the 4 range, maybe some in the 3 range. However, the pKa of a dicarboxylic acid, that first pKa, it's actually going to be pretty low. It's actually quite acidic compared to anything we've seen so far. It's going to have a pKa of approximately 1.2. Okay, so this is low. Now, of course, if we're introducing something that looks quite different from what we've seen before, we got to ask ourselves why. So why is pKa1 so low? All right, we have a couple of reasons. First, like I mentioned, we have 2 acidic protons. So statistically, it'll be a little easier to find an acidic proton and remove it. So we have 2 sites for deprotonation. And now a second reason, we need to think a little bit to what we were talking about earlier. So we recall that whenever we introduced a more electron withdrawing group, or in the case where we just had an sp3 versus an sp2 atom, we were introducing a little bit of an electron withdrawing effect, okay? Now in this case, we have a carboxylic acid that serves as the electron withdrawing group for the other carboxylic acid, okay? So we see that one carboxylic acid is the electron withdrawing group for the other one. All right, and as such, we're going to see a strong electron withdrawing effect. And the fact that that carboxylic acid is so close, and we have 2 electronegative atoms on there compared to just a regular benzoic acid, we're going to see quite a significant shift in pKa compared to what we saw previously, okay? So that's why you would expect that first deprotonation of a dicarboxylic acid would actually be quite facile, which is why you'd have such a low pKa, making it more acidic. Now, as I mentioned, we have 2 possible pKas here, okay? Now, in this case, this intermediate species that we are generating is not symmetrical anymore. We have one side that is protonated, that has an acidic proton, the other side does not. So if you were to go and then bring in some sort of base to deprotonate a second time, let's say we added in some more water here, we see a different pKa. And that pKa actually is a little closer to what you would normally expect, 4.3. Still lower than acetic acid, but relatively closer to acetic acid than that first pKa. And doing so, you end up generating a dianion with 2 hydroniums acting as the counterion in this case. All right, and for that pKa too, we could attribute that pKa being higher than the first one to we already have a negative charge on the molecule, so introducing a second negative charge will probably be a little more difficult. And then also that carboxylate that we have is now our new electron withdrawing group. So this one over here, for the new carboxylic acid that we're deprotonating. And carboxylates are actually not as electron withdrawing as just a regular carboxylic acid, okay? But what's really, really important and what drives this point home is the fact that that pKa1 is so low for some of the reasons that maybe weren't as obvious to you now, but drawing back to what we were talking about earlier, now makes a little more sense. Okay, so at this point, I'm going to draw the line for content for exam 2. So everything that I have talked about now is basically all the content that you will need to know for exam 2. All the new content you need to know for exam 2. From now, we're going to do a little bit of review of older content, and we're going to be comparing and contrasting some mechanisms. In practicing in OLS and on your own in homework and whatnot, you're actually going to see that some of the mechanisms may be relatively similar, but some of them may have a little bit of nuances that could make them a little tricky. So we're going to talk about two mechanisms that are similar, but have some specific differences based off of things like the nucleophilicity of our coupling partner, and also the number of proton transfers and where the proton transfers are. Yes. Yes. So pKa1 is going to refer to the acidity of the first proton that we were removing. Okay, so that pKa1 refers to the removal of the first proton. So essentially, when we're referring to pKa1, it is the pKa of this acidic species, the dicarboxylic acid. pKa2 is now the pKa of a separate species, a very similar looking species, but a separate species that now refers to the carboxylic acid with the carboxylate in the same molecule. Great question. Any other questions before we move on to a little bit of review? All right, so now we're going to go and compare and contrast the mechanisms of acetal and ketal formation. Sorry, and imine formation. Okay, so these are going to come from learning objectives 18I and 18L. Okay, so I'm going to draw these mechanisms somewhat side by side. So for acetal formation, if you want to look at this in the textbook, this is going to come from section 18.8. And in the case of your imine formation, this will come from section 18.10. So in both cases, in acetal and ketal formation, you're going to have an electrophile, which will be a ketone or aldehyde. In this case, I'm going to use an aldehyde because it's going to drive an important point eventually when we're talking about imine and enamine formation. And we're going to have a nucleophile. In the case of acetal formation, the nucleophile will be some sort of alcohol, so in this case, methanol. In imine formation, you're going to have a primary amine, which is just an amine that is bound to one other carbon, okay? So here we have methanol and we have methylamine in each respective case. If we're thinking about the general reaction scheme, the specific conditions that we use certainly matter. In the case of making an acetal, we're going to need to introduce some sort of an acid. And in the case of an imine, we'll have some acid in solution as well, but it'll be very, very weakly acidic. So the pH, it's going to be pretty close to neutral. It'll be a pH of approximately 5. Now, combining these two, so you know that this carbon in the middle is going to be your electrophilic carbon. So when we're drawing the mechanism, you're going to see that that's the carbon that gets attacked. We're going to end up with our acetal, which looks like this. And then you're going to have water as a byproduct. Through a very similar mechanism, but not exactly the same mechanism, imine formation will form an imine that is a carbon double bound to a nitrogen, which has some other carbon base group that is bound to it also. And in the same fashion, we are also going to be generating water as a byproduct as well. or the oxygen in water comes from that original carbonyl oxygen. So that carbonyl oxygen needs to leave at some point. And that central electrophilic carbon remains as that center of the structure that you will have at the end. So I just said a few things. So let's actually go and do a little bit of a more in-depth analysis and see exactly why the conditions are going to be a little different for each case. Now, as I mentioned already, the general mechanism is about the same. Okay, in terms of what we are trying to accomplish with each step of the mechanism. All right. The first step is going to consist of your nucleophile attacking your carbonyl. All right. So in the case of the acetal, that adduct is going to look something a little like this. And in the case of your ketal, that same adduct, or the analogous adduct rather, and I keep saying ketal, I'm sorry, this should be imine. Will look like this. So after a few proton transfers, this is the adduct that you're going to get with the nucleophile attacking the carbonyl. And this will be a very, very important intermediate in either mechanism, because this is the last intermediate that you're going to get before you go and then effectively generate either your final product or a version of what looks like your final product. Now, the second step is going to be that the lone pair is going to push down and the carbonyl oxygen will leave as water. All right, so in either case, you have a leaving group, the same leaving group, that being water. And what you want to look for is this oxygen that is bound to the carbon that's bound to water, or this nitrogen that's bound to the carbon that's bound to water. Okay, again, pattern recognition, same thing in either case. We're going to take a lone pair on each of those species and just kick off our water. And doing so will generate your subsequent intermediates. Okay, so these are some important steps to look out for in either case. Now let's talk about the differences. Okay, so these are essentially the similarities that each mechanism has, but how you get there will be slightly different. And these differences will lie in the proton transfers. Right, so again, we're going to do a little bit of a side-by-side for acetals and imines. So again, we have our electrophile, which is the same in this case over here. And first big difference is the nucleophile that we're going to be using, okay? So I mentioned that we had either methanol or we had methylamine. Now, these two nucleophiles have different strengths, remarkably different strengths, okay? Particularly the alcohol is a weaker nucleophile, and the amine is a stronger nucleophile. Now that's important because if your nucleophile is weak enough, it will not be able to attack just straight up as is, okay? And in the case of methanol, we have an oxygen that's too electronegative to be able to just attack as is, and is also neutral. In the case of the amine, the nitrogen is a little less electronegative and more willing to give up its electrons. So you don't really need any activation, okay? Now we need to activate our carbonyl in the case of the methanol. In order to make the nucleophile better. And that's why we need the acid. Okay, so here we use tosic acid as our acid source. And we start by taking a lone pair on your oxygen and removing a proton off of your tosic acid, okay? When you're doing a reaction in strongly acidic conditions, your first step will generally be to go and protonate your carbonyl, because typically the nucleophiles that you're using will not be that strong. Okay, so any oxygen-based nucleophile will have this first step under acidic conditions, because that nucleophile is initially neutral and hence not that strong. So now we end up with now we're going to end up with this protonated carbonyl, okay? So in order for that nucleophilic attack to happen in the case of methanol, in order to form your acetal, you will need to go and then protonate that carbonyl first to make that oxygen positively charged. And now that carbonyl is electrophilic enough with the nucleophile that we're using in order to go ahead and carry out our desired attack. I will also note here that in this step, we have gained a hydrogen. It'll be important later. Or gained a proton, rather. Okay, so now it is time for us to go in and add in our nucleophile. And I'm going to do the same thing in the bottom as well. Now, our nucleophiles are both strong enough to attack our carbonyl in either case. Make this like this. And this is the adduct that you get after the addition of your nucleophile in the case of the acetal, and this is what you get after addition in the case of the ketal. Okay, so in the case of, sorry, I keep saying ketal. In the case of the imine, you're actually going to see that you have a negative and positive charge both on the same molecule, whereas here you just have a positive charge, so you're going to need a counter ion, in this case, the tosylate. All right, now you're going to see that we're going to take this proton and remove it. So now at this point, we're going to lose a proton. And then we're going to have a proton transfer step. In order to go and generate that same intermediate that we saw on the previous slide. And at this point, you see that now our carbonyl oxygen, our original carbonyl oxygen, has gained another proton. Now let's see what happens in the bottom case. So in the bottom case, again, we do have to lose a hydrogen in the same case that we saw in the acetal step. And through the conditions that you need in order to form your imine, you will then have two subsequent proton transfers. Where you gain two protons. Now, this can be a little bit of a point of confusion because what really makes the difference between these two mechanisms is the order of the proton transfers that you're doing. Okay, so essentially you have the same number of proton transfers, but the order is different. Okay, so in the case of an acetal, essentially the order of the proton transfers is going to be gain, lose, and gain a proton. In the case of the imine, you're going to lose a proton, and you're going to gain, and then you're going to gain another one. And this, again, is attributed to the conditions that we're running these reactions at. So be very careful with the conditions and the proton transfers that you're using when you're drawing this type of mechanism. All right. So now continuing on with this. Again, using the same intermediate that we had previously. We're going to go and then take our lone pair and then expel off our water, which again is the leaving group that we have in this case. So as I mentioned earlier, these two steps are the same. But now the difference that we're going to be seeing in this case comes from what we do from here. Okay, as what happens now is that we do have a proton to remove in the case of our imine, but in the case of our acetal, there is no proton to remove. Okay, so what happens now? Well, in this case, this is where we're going to take our second equivalent of our methanol. And then attack in order to go and then generate our protonated species. That precedes our acetal. Whereas in the case of our ketal, in the case of our imine, we're going to have another proton transfer that will go and then give us our final neutral imine. Here we do still have one more step, another proton transfer in the case of our acetal. And we have finally gone and we have generated our acetal. And in this case, our imine. Both of these are stable neutral molecules. All right, any questions about these mechanisms? Okay, so I hope you all enjoyed today's lecture. As I mentioned, there is a feedback form that I